Let's record. All right, so we're going to start again. So, all right, good afternoon or morning, everyone. Thank you again for taking this time to join this online presentation. My name is Raj. I work for Rapid Tech Equipment. Rapid Tech Equipment is one of the main distributors of test and measurement equipment in Australia, with offices in Melbourne, Sydney, and Brisbane. We are also the largest distributors of flare thermal images. And obviously, this is what has led us to organize this online presentation. Today's topic is more about getting to know thermal images by understanding the basic principles of thermography. All right, so hopefully this will make everyone a bit more comfortable about using this technology for whatever application you may have. All right, you will, hopefully at the end of this presentation, you'll see it's thermography is not rocket science. It's quite a simple technology to understand. And then at the end, I will just introduce some of the ranges of flare thermal cameras or thermal images, starting from entry level to a professional series. So if you have any questions during the presentation, please don't be shy to ask. All right, so let's start. So what is thermography? Okay, I mean, thermography, this slide explains the biggest difference between really photography and thermography. I mean, it's quite obvious. We obviously know that photography, it's related to light, okay? Whereas thermography is related to heat, or you could say the scientific term is infrared energy, okay? Which is then converted, that infrared energy is converted into a temperature value. All right, so that's thermography. The definition of thermography, all right, is capturing thermal information using a non-contact device, such as a thermal imager, and then performing some sort of analysis. All right, so in simple terms, a thermal imager, all right, such as this, is made up of multiple pyrometers, which read infrared energy and converts this to a corresponding temperature value, okay? And in turn, this temperature value is represented by a color palette to give you more a visual display. All right, so if you guys all know, an infrared thermometer, okay, simple infrared thermometer. That's just a single pyrometer, all right, that's just looking at one temperature value, all right, and all it's giving is a, one single temperature reading, okay? So whereas a thermal camera, all right, something like this model here is it's made up of around 76,000 sensors, all right? So it's reading multiple temperature values. So they work very similar, but obviously with a thermal camera, because you've got multiple sensors, you can obviously create now a heat map, all right? And so that gives you a visual display. So, and depending on the color palette, but in general, the darker the color, all right, the cooler the temperature, and the lighter the color, the warmer the temperature. All right, so why is thermography so important? Here are some of the main reasons. Obviously, it is a non-contact method of testing. Okay, so this allows you to make any measurement or analysis from a particular distance, and maybe it's a safe distance. All right, so like high voltage applications in a switchyard, where so you need to stand at a distance, okay, or high voltage switchboard. So that's one importance. Second importance, it's always easy to understand something with a visual display. All right, gives us more information. Again, going back to the, a simple IR thermometer versus a thermal imager. All right. Just that visual display just gives us more information. The other important is obviously it's done in real time. Okay, so the information we're getting is in real time. So any answers can be determined then. And there's not a lot of post analysis required. Unless you download it to the software and do post analysis that way. And then lastly, thermography can be used for qualitative or quantitative analysis. And I'll explain that a bit more in the next slide. All right, so just go back. All right. So what is the difference really between quantitative and qualitative analysis? Okay, so qualitative analysis relies on thermal patterns to find your anomaly. All right, so all we're doing is we're just looking at the colors, all right, to create a thermal image. All right, whereas quantitative analysis is actually using temperature readings, which we also get to receive from a thermal imager. So example, if you're running, there's a motor running, all right, and if it's above a certain temperature, all right, so that's when you can use a thermal camera to do a quantitative analysis. Whereas if you're, let's say, looking for water leaks behind a wall, okay, it's not much about temperature you're trying to read. It's more now you're doing a qualitative analysis because you're looking at a color difference. All right, so I'll go through some examples very shortly. But I think it's when you start thinking more qualitative analysis, it just makes using a thermal imager very easy because it's not really about capturing all those temperature values. It's about just looking at the image, the visual image. And as we know, visual image can say a lot more. So some examples here in the next slide you will see. So here, this is the top two images. Okay, I mean, pretty much all the images, you can utilize qualitative analysis. Okay, so you can see here the levels of tanks. Okay, so we're not getting any temperature readings here at all. Even this tank here, we can just see the different levels. Okay, in this case, with this motor, obviously we can use qualitative analysis. So just looking at the color difference between this motor and the other motor and seeing that this is running hotter than the other. But obviously the temperature value in this case, quantitative analysis, is just showing us pretty much maybe the severity of how hot this is running. So, and that's where you can kind of utilize that quantitative analysis. Again, this example here, okay, if you apply qualitative analysis, all right, it's all just looking at color difference. Okay, you're going to see that this connection here, the electrical connector, is running a lot warmer than these phases, these other two phases. Okay, so again, then we can, if you apply the quantitative analysis and you get a temperature reading, it's just looking and going and seeing what temperature value it's actually running at. So that's the biggest difference between qualitative and quantitative analysis. So just moving over to the next slide. So we're just gonna get into a bit of science, going back to the good old school days, and just touch on a bit of infrared radiation, because I mean, that's how thermal cameras work. So if you understand a bit about infrared radiation, then it'll give you a better idea of how the thermal cameras work. So to understand infrared, we need to start back with the electromagnetic spectrum. All right, so most of you would have seen this electromagnetic spectrum, you know, UV, visible light spectrum, you've got the infrared, the microwaves, okay, and then RF. So we all know that the visible light spectrum is part of the electromagnetic spectrum. So our eyes can see this visible light. So our eyes are acting like detectors, and that's all we can see. We can only see this part of the electromagnetic spectrum. So around, you can obviously see around the visible light spectrum, there are different types of spectrum, and just above the visible light spectrum is the infrared spectrum. Okay, so it's there, all right, it exists all the time. It's just that our eyes cannot see it. And this is where thermal cameras come into play. They can detect that infrared spectrum beyond the visible spectrum. Okay, so every surface is emitting infrared energy. All right, so whatever the surface is, whatever temperature the surface is sitting at, it'll be emitting that infrared energy. All right. So our question is, example is our bodies, do they emit infrared energy? And the answer, simple answer is yes. Our body temperature is at 37 degrees. So our body surface temperature is around 33, 34. So if you were to, you know, point a thermal camera at a person, you will see that infrared energy. All right. I mean, using our eyes, we can't obviously see it, but the thermal camera is picking that infrared energy that is being emitted from our body surface, our surface temperature. So, all right. So that's where the infrared spectrum fits into. Okay, just above the visible. The other thing to understand is modes of heat transfer. All right, and this is linked back to the fact that, all right, with any technology, there's some sort of limitation. All right, and thermal images have a limitation. Okay, I'll touch a bit on that, the main limitation, but if you understand modes of heat transfer, that will help us kind of work around that limitation. Okay, so there are three modes of heat transfer. All right, the three being radiation, convection, okay, and conduction. All right, so radiation is it's energy that is radiated. Okay, in this case, you can see in the form of heat. All right, that's radiated through the atmosphere. Convection is obviously the heat that's transferred through a liquid. Okay, and the most important heat transfer to understand is conduction. Okay, and that's that's the transfer of heat from one substance to another from purely direct contact. So like I said, if you guys can keep that in mind, these three heat transfer, because when we come to the next slides, you will see there is a limitation with thermal images, and that's when we can then apply these concepts to work around that. Okay, so let's see it. So emissivity, this is probably the most important concept to understand when you're using a thermal imager. Okay, so what is emissivity? Emissivity is pretty much the ability of an object to emit infrared energy in comparison to a black body. So a black body is a perfect emitter, or you could say an emissivity of 1. Okay, so opposite to a perfect emitter or a black body is a perfect mirror. So what that means, it reflects all its infrared energy. And now that has an emissivity of 0. So emissivity is a number between 0 and 1. All right. So 0 being a poor emitter of infrared energy, and 1 being a good emitter of infrared energy. The way I tend to remember it is 1 meaning that it's 100% of its infrared energy is being emitted from the surface. All right. Whereas at the other end, 0 means 0%, okay, of its infrared energy is being emitted. So I've got a good example that I can show here. So I'm going to just switch cameras. Let's bear with me. Switch over to, just going to set up this camera here. So I'm not sure if you can see. All right. So what we've got here, I've just plugged in an iron. So this iron over here. All right, that's it's on at the moment. Okay, and I've got an aluminium foil covering half of the iron, with the other side, which has got a Teflon coating, is exposed. Okay, so if I was to show a thermal camera, all right, so at the moment it's obviously hot, so we don't want to touch it. But if I was to show a thermal camera, so let's just bear with me, I might have to. Just get a bit closer. Okay, so just play around with this. Okay, so you can see, everyone can see this image. All right, so like I said, the iron's turned on. It's a bit out of focus. Okay, there we go. The iron's turned on. We can see the left side. All right, it's well above 150 degrees. Okay. Whereas the right side with the aluminium foil, it's only showing around 30 degrees. Okay, so the reason why, the left side, we're now working with a surface which is emissivity close to 1. Okay, so because it's got an emissivity close to 1, it's emitting its true infrared energy. And this is where the camera's picking up that infrared energy. On the right side, all right, we've actually changed that surface property, all right, by putting the aluminium foil. So we've actually now reduced the emissivity value close to 0. So as a result of that, all right, the thermal camera is not picking up any infrared energy because that infrared energy is not being emitted. But if you were to touch that side, the aluminium foil, it'll be still at the same temperature of about 145, 150 degrees. But that's just showing the difference, or what emissivity can have, the effect of emissivity. When you have a surface which has got a poor emissivity value, a thermal camera is limited, okay, in picking up that infrared energy. All right, so that's important to understand. So I'm just gonna switch back to, just bear with me. So yeah, so every surface has got an emissivity value. All right, like I said, between 0 and 1. So I think if fact, I'm just going to scroll through a bit more. I'm not sure if you guys can see this. I mean, you can find this online. It's a table of emissivity values. And pretty much the rule of thumb is any shiny metal, anything reflective, any reflective metal or anything like that, you know, or even glass. All right, you've got an emissivity of close to 0 because it's more reflective. So things like, you know, shiny copper, aluminium. So that's the rule of thumb. So anything which is a shiny metal, a thermal camera is not going to pick up its infrared energy that's being emitted from that surface because it's got an emissivity of close to 0. So things like, but if you've got a surface like a shiny metal, if you were to look at the emissivity of black tape or even paint, all right, you will see the emissivity can change. Emissivity of paint is close to now 0.9, 0.95. Black tape is 0.95. So by just changing that surface property, by applying black paint or a tape, gaffer tape onto that surface, you're changing the surface property. And because of that, that surface is now going to emit its infrared energy. And that's when the camera will then, thermal camera will pick that infrared energy up. All right, so yeah, again, there's limitations, as I mentioned, with thermal imaging, but there's ways to work around it. Okay, and that's obviously, if you can change the property of the surface, that helps. All right, so if you go back a few more slides to here, we've got, like I said, good emitters. All right, so anything electrical insulators are obviously good emitters. So these have got the high emissivity value. All right, so you've got wood, plastic, as I mentioned, painted surfaces, rubber, PVC, concrete, all right, paper, tape, which hasn't been included in there. So they are good emitters or good high emissivity values. And then if you look at the other end of the spectrum, poor emitters or low emissivity, that's, you know, close to 0, 0.1, thereabout. Copper, iron, nickel, yeah, anything metal. But even with these type of metals, if you start looking at oxidized surfaces, all right, anything that's been oxidized, all right, that starts to improve the emissivity value. That starts to increase the emissivity value. All right, so if you're ever looking at that table again, they'll have emissivity values for just shiny copper, and they'll have emissivity value for oxidized copper as well, which you'll see the difference in the emissivity value. Okay, it makes a big difference. So, all right, so like I said, emissivity is very important to understand. It's knowing what type of surface you're looking at, all right, and knowing, you know, a rough idea, is it got a low emissivity value, all right, or is it got a high emissivity value, okay? Because, you know, sometimes you can get, you know, instances like this where, you know, you're looking at something that's reflective, all right? In this case, you know, something like this iron, and it's showing there's something hot, there's a hot spot there, but it's purely reflective, all right? So the actual iron surface is not emitting its infrared energy. The infrared energy is getting reflected from a different source. Okay, and in this case as well, if you were to ever stand in front of a glass window, all right, and point a thermal camera, all right, you're not going to be able to see through the glass window, but you'll be seeing a reflection of your body temperature, that infrared energy that's being emitted from yourself, and it's bouncing off the glass, and the thermal camera is picking it up. Okay, so that's it. Like I said, a very important thing to remember is emissivity. Okay, so let's go into the next slide. Whoops. All right, so when taking an image, things to take into account, all right? Like I mentioned, the knowing the emissivity of the surface. I think that's the important thing to understand. Obviously the distance, okay, and that's to do with something I'm not going to touch. It's a bit more complex to understand. It's something to do with called milliradians, and that's coming back to resolution. So it's a distance to take into account. Image composition, focus is very important, because if a camera is out of focus, all right, so your temperature value can be out by 3 or 4 degrees. But again, if you're doing qualitative analysis, okay, focus is also important. So correct temperature range, all right, so making sure you set on the correct temperature and you're not getting saturated colors, okay. And other, like I said, other factors to look for is reflected temperature. So obviously understanding what other heat sources are around you, because they would be emitting some sort of infrared energy as well, all right, and they may be contributing to whatever surface you're looking at, all right. So just understanding what kind of environment you're working in, and obviously the atmospheric temperature, which plays a small role. So this is obviously working under, in warmer conditions, things like that. So if we go to the next slide. So I'm just going to go through some of the main applications. Obviously, thermal images, can be used in a lot of applications, and there's always new ones that we come across every year. Obviously, the main application, which pretty much maybe started thermal imaging, thermography, was electrical applications, using in switchboards. Okay, so these are some classic examples here, where you can see, connection of a fuse. Obviously, it's creating a hotspot. Again, it's a qualitative analysis here we're looking at. Okay, that we can see that one fuse, ceramic fuse, is running a lot hotter than the others. Okay, so it's a comparison here we're making. So it's not really about the temperature values, but it's about the comparison. Again, we're looking at some fuses here as well. Okay, like I said, it's qualitative analysis. Temperature is more important if you want to see the severity or the extent of the actual, issue. Here again, we're looking at some sort of a connection problem here, a loose connection maybe, all right, that's creating a centralized hotspot, okay, and you can see that obviously getting transferred through to the wires, okay, and again, we've got here some sort of a high resistance, obviously a poor connection that's creating some sort of heat, okay, and that's again, we're doing a qualitative analysis. Okay, so going back to actual emissivity is something I did. I'm just gonna swap over to the camera. So I'm gonna try this again. Let's see. Sharing. Let's go back to the camera. Just want to kind of touch base on the heat transfer. So just gonna move around. So I've got a wire here, obviously, that's got exposed copper. Okay, it's got an exposed copper, and it's just insulation. All right, so I've got so what I'm going to do is I'm going to heat up this. Just going to heat up this the copper cable. Okay, so just going to give it some time to just heat up a bit. So I'm just going to move that aside now. All right, so not sure if you can see this, but I was to move this cable close. So you can see what's happening here is the copper cable, okay, it's not showing a hotspot, all right, because it's got a low emissivity value, all right. Whereas if I move over to the actual insulation, all right, we're actually now seeing the infrared energy being emitted. And that's because, again, it's to do with the emissivity of copper. It's a lower emissivity value versus the emissivity of the actual insulation, which is a high emissivity. So this is now we're applying what I spoke about before about the heat transfer. So this is conduction. So we're going back to conduction. So obviously this hotspot here, this heat here has been transferred through to that insulation there. So we can't actually see the infrared energy emitted from the copper, but we can actually tell by the insulation that it's a lot hotter. All right, so that's giving us an idea that there may be some sort of a loose connection. Okay, so hopefully that makes a bit of sense. If I go back to the slide, share it. Sorry, I need to share. All right, so we go back to this slide. So like I said, so in this case, we're looking at some examples here where we can see that the heat is getting transferred through to the cable. Okay, so obviously there's nothing really, these aren't probably best examples. There's nothing really shiny. Well, yeah, these, well, here actually, good example is here. All right, so where the fuses are connected, you can see that, just above that, obviously it's very hot, whereas where the metal, all right, it's got a low emissivity value, all right, so it's not giving us, it's not showing us the infrared energy that's being emitted. So this is where we've applied, conduction to kind of understand that, there's obviously some sort of a loose connection that's happening there. So again, some of the applications, like I said, loose connection. All right, so again, so this is a metal that's obviously it's got a low emissivity value. Where's this surface here? This is obviously maybe some sort of a crimp. Okay, that's actually got a high emissivity value, so it's actually emitting its infrared energy. So the thermal camera can actually see that there's something occurring here, that there must be a loose connection that's creating a high resistance, and that heat, because of conduction, is getting transferred through the cable. Okay, so another application, obviously motors. All right, so we're looking at bearing issues or winding issues. So anything mechanical. All right, misalignment. All right, so this one here, this is obviously showing a misalignment. Okay, so that's another application using a visual. Okay, conveyor belts. All right, so we're looking at conveyor belts there. Again, we've touched base on this one before. So the doing qualitative analysis, just looking at levels of tanks. Okay. Again, automotive, so used mainly in the automotive industry. So it's another application there. Yep, pipes, seeing deterioration of pipes. Okay, or any tubings. So these are just some examples of, obviously, so in the medical industry as well. So we can use these to kind of look at, body temperatures. Some hospitals use for research, they use thermal cameras to look at blood flow as well for, for diabetes. that kind of application. So one of the main application at the moment that thermal cameras are being used are for building diagnostics. All right, so we've seen there's a bit of a shift in you could say the use of thermal cameras. We're seeing more thermal cameras being used in the building industry than actual, you could say, the electrical these days. So thermal cameras can look for, damp areas or, water leaks, missing insulation. All right, so it's a big application there, the thermal cameras, and that's building it all purely qualitative analysis. All right, you can see all these images. There's no temperature values at all, because all you're looking at is just a color difference. Okay, looking for cold versus hot. And as I mentioned, cold is it's a darker color, so it's a purple, and warmer is the lighter color, which is the yellow. So yeah, definitely a big industry for thermal cameras. Termite inspections, okay. Again, that's part of building. So, we're not using thermal cameras to detect individual termites, but looking at nests. Okay, so this is obviously picking up a nest. This is picking up an array of obviously termites that are moving around behind this wall. Okay, so yes, definitely so a lot of the pest inspectors, they've most of them have got obviously thermal cameras. They're using thermal cameras to help them detect any termites. Again, so we're touching a bit on the buildings, so missing insulation, solar. So obviously the solar industries can use thermal cameras to look at, damaged solar panels. Okay. All right, again, missing insulation. All right, so that's second image is showing wet bricks. Obviously, you can see that. And the thing to understand is, again, so the thermal camera is purely looking at the surface temperature. All right, it's not looking beyond the surface temperature. It's just looking at only the surface temperature. So whatever's happening behind, these surfaces, okay, as long as that is changing this surface property, that's when the thermal camera will pick that up. All right, so again, yes, there is some sort of a limitation when it comes to, in what you can detect. Obviously with the building application, if you're looking at, looking for water leaks, and the water is, the leak is well behind the wall and it's not changing the surface property, then the thermal camera is not going to pick it up. Okay, so last one was a hot pipe. You can obviously see this. So someone's running a very hot water through the pipes, and the thermal camera has obviously picked that up. Okay, so the key things when choosing a thermal camera, obviously, is a temperature range. Okay, and this is all to do with the temperature range you're working over. All right, so some cameras have a range of 150 degrees. They've got 400 degrees. You can go up to 650. You can go up to 1,500. So depending on the actual temperature range you're working over, resolution is very important. Okay. So the 80 by 60 resolution is classified as a low resolution, because if you times that out, that's 4,800 pixels. All right. Whereas you move up to a 320 by 240, you're working with now 76,000 pixels. So obviously you get a lot more information with a high resolution camera of 320 by 240. And it's depending on the type of things you're looking at. If you're looking at for electrical, a lot of small components, all right, resolution is critical. All right, so you can actually, pick up any temperature changes. Thermal sensitivity, I think, is more important for building application. All right, because you're working over a narrow temperature range. When you're looking at building, you're only working over ambient. and you're looking now for very small temperature differences. So thermal sensitivity is more a big requirement for a building application or pest, you know, when you're looking for termites. So, and then the last is obviously onboard functions. So things that, you know, you may find to make your job easier. You know, some of them have got, you know, ability to record notes, video capture, things like that. So, you know, some people might not find them useful, but, you know, in certain situations, you might find it important to help you do your job. So, all right, so that's the end of the slides. All right, I'm gonna now probably go through, I'm going for time, so yep, just enough time to kind of just go through some of the basic, or the range of thermal cameras. All right, so just gonna set myself up here. Okay. We've got a few of them here. Okay, so I'll start with the entry-level series, which is Flare C5. Okay. So this thermal camera is a pocket-sized thermal camera. Okay. When it came out, it came out for the building industry because it's small in size. It's got a resolution of, it's a mid-size resolution, so 160 by 120. Okay, because like for the building industry, you know, resolution is not as critical as what I mentioned at thermal sensitivity. So with this camera has got a thermal sensitivity of 0.07 of a degree. So that's the smallest temperature that each pixel can detect compared to the other pixel. All right. So this one is a new model. So it's got probably kind of the latest technology, meaning it's got touchscreen as well. This one is also got the capability of, when you take an image, you can actually write some notes down. Obviously, being touchscreen, that's obviously an advantage. It also works with the new FLIR Ignite, which is a cloud software, cloud-based software. So it's so if someone's out in the field and they're taking thermal images, all right, so you can automatically upload it to the cloud system, whereas then when someone back in the field and back in the office can start generating reports straight away, okay, without having the camera back in the office. So it has got some of the latest technologies. So this camera sits around the $1,200. So it's nice and compact, very easy to use. Okay. And it's a good starting point for even for electrical applications as well. You know, if someone's starting off and they want to, you know, kind of just start off with something simple, something easy to use. All right, it's also a good starting point. So that's called the FLIR C5. It's nice and compact. Okay, it's got a built-in rechargeable camera, rechargeable battery. Okay, so you could probably say that's probably one of the main disadvantages. Obviously, something having an internal battery, you know, once the battery goes, then it becomes a repair issue. And obviously, you know, if the charge, you know, you lose your charge, then you've got to try to find a place to charge it up. Okay, so that's the FLIR C5. All right, the next step up is then the EX series. All right, there's really four models in this range. Okay, this is the top end of the model. It's the E8, but there's the E4, E5 XT, E6 XT, and E8 XT, which is this model here. Okay, ergonomic design because it's for one-hand operation. Okay, so You can see one hand operation there. You've got the trigger button there, just on your index finger, ready to go. Okay. Whereas going back to the C5, this is a two-hand operated unit. All right. So you've got one finger on this button here to capture your image. Okay, and the other hand just holding. So with this one, you just got to make sure you have a bit of a steady hand. All right. If you haven't got a steady hand, then yeah, you'll find a lot of your images will be out of, they'll probably not be in focus. So going back to the EX series, like I said, yeah, it's got slightly better image quality because it's got a better digital filtering, better temperature stabilization. Hasn't got the latest technology as the C5, so it's not touchscreen or anything, but it's very easy to use. All right, so it's just you know, navigating using these soft buttons here in the front. It's got a removable battery as well, so that's one big advantage. Okay, so you can obviously, you know, take that out and swap it over if you've run out of charge. So that's the EX series. And then you go into the EXX series. So, oops, I should have set this up. This is so this is now moving into the professional series, all right, where you're getting a lot more capability. And that includes things like video capture. Again, it's got the touch screen as well. Okay, it's got you could say more sharper image because it's got a narrow field of view. All right, so with these entry-level series ones, the EX series, okay, if you look at the image, you've got a wider field of view. All right, so which, you know, for a lot of applications, you know, it can be useful, especially for building. So with this one here, if you want a more detailed image, all right, you can see that you get a lot more detail in what you're looking at. And with this series, the professional series, you've got the option of changing the lenses as well. So at the moment, this one, it's got a 24-degree lens. Okay, so you can change that to a wide angle, so 42 degrees, or if you want to work at a further distance, you can actually change it to a 14-degree lens as well. So you've got that option. Again, yeah, you can also, you know, make any voice annotations against the image with this model or this series. It's got built-in laser as well for guidance. Okay, so it's got all these extra functionality just to allow you to do your, you know, do your job a bit easier when you're out in the field. So, and again, yeah, removable battery as well. So that's the EXX series. So this it starts with the E54. So the E54 is the entry level one, which has got purely a manual focus. Okay, and then you can go up to the E76, E76, E86, and E96, where you're now introducing autofocus as well. And you've got slightly higher resolution as well. So, and a higher temperature range. So these are the three main range of flare thermal cameras. All right, and it all depends on, you know, what the application is and what you're after from the thermal camera. So so that's it for our presentation. Hopefully you guys have taken a bit of information away from that, and if you've got any questions, yeah, please feel free to ask. Thank you.
Raj, this is Nitin here. I think very nice presentation, very informative. Thanks very much for that. Now, I work at Victoria University, a uni, and we are trying to do some, you know, we got a green roof, and we are trying to see you know,
sorry, start again. Sorry.
Not a problem. I'm Nitin here.
Yes, hi Nitin.
And I'm looking at using the green roof, the thermal camera at a green roof on our campus. So we are looking at a big area, maybe 10 meters by 5 meter kind of.
Okay.
Now, to use the camera for bigger areas, what's the criteria to use? Is it the resolution?
It's dependent on what you're trying to find. So yes, resolution is important, and that's linked to field of view. So because you're looking at a larger area, you need a very wide angle field of view. So as I mentioned, 42 degree. And because you're working with a wider field of view, resolution is important, because now you're going from a narrow field of view to a wider. So your pixels get spread out. So it's a combination of both. You need a wide field of view plus a high resolution camera.
Okay.
So what is it when you said a green roof?
What we are trying to see is trying to look at different materials on the roof and look at its ability to cool. What's called green roof, cool roofs. We can have different cooling paints available in the market.
Okay.
And then trying to see which one would cool the roof more.
Okay. So if you use something like an E8, which has got a wide field of view, what you will see is, I'll show you the difference, is you lose a bit of the detail in the image. All right. Whereas if you use something like a E76 with a 42 degree lens, all right, you'll see more detail in the image. So I think, and that's what you're after, isn't it? You're trying to capture more detail in what you're looking at.
I mean, detail, yes, but we are also trying to look at capturing the differences in temperature between the materials on the roof. Okay.
If you want to just see the difference of material, then something like an E8 will do that job. All right.
Okay.
Because it'll show one material might be hotter than the other. But if you want to get the detail, that's when you need to go to the professional. All right.
Okay.
So it really depends on what you're after, what kind of information you want to get out of the thermal camera.
Right. Okay. I'm looking at the temperature differences actually.
Okay. So something like an E8, which is around the 4,500. Okay. That will do the job.
And the professional one you said,
the
just
E76 is around the 10.5.
Oh, 10.5. Okay.
All right.
Thanks, Raj. Thank you very much.
No worries.
Raj, I need to leave. I'll excuse myself.
Okay, that's fine. Thank you.
Thanks very much. Thank you.
So is there anyone else with any questions or? All right. Well, I'm going to stop the recording.